Today we are going to talk about calculations involving colligative properties and specifically calculations of the freezing point depression and boiling point elevation for solutions based on how much solute there is in them. Before we do that, however, we need a new unit for concentration because colligative properties can involve changes in temperature, and molarity does not change. Molarity changes with the temperature, so we're going to define a new unit of concentration called molality. Molality is usually given by lowercase m, and in cases when I can type this out, it will be italicized. It's very similar to molarity. It involves the moles of solute in the numerator, but now instead of the liters of the solution, we're going to have the kilograms of the solvent. And as I said, this solves the problem of dealing with changes in temperature because the kilograms of solvent does not change when the temperature changes. So molality calculations are very similar to molarity calculations in that we're going to take, the only thing that you have to watch out for now, we're going to take two masses. We'll have the mass of the solute, and you can tell it's a solute because we're going to say this is in, so that means that this is going to be the solvent that we're putting it in. And also, whenever you see water, you're going to know that that's a solvent. We will deal with non-aqueous solvents in this as well, because there's a chance to use them in this part of the unit as well. So, knowing that we need the moles of the solute, we're going to calculate the moles of the KBr. And we're going to take our 80.0 grams of KBr. And little dimensional analysis, 1 mole KBr. And I'll spot you the molar mass, 119.0 grams of KBr. 4 sig figs is enough for us. And that's 0.672 moles of KBr. Also remember, we've got to convert grams. I say remember, you're just finding this right now. Make sure we always convert to kilograms. So 500 grams multiplied by 1 kilogram over 1,000 grams. And we get 0.50000, yes, oops, sorry, too many zeros, 3 zeros, kilograms of the solvent H2O. So then the molality, M, is just 0.672 moles divided by 0.5000 kilograms. Dividing by 0.5 is the same as multiplying by 2 if you want to do this quickly. And that gives us 1.34 molal. M for molal, like molar, but with an L at the end. And as with molarity, if we need to find the moles or the grams, the reverse is going to be true. Just rearrange the equation, and we'll find that the moles of solute is equal to the molality times the kilograms of the solvent. You could also, again, find how many kilograms of solvent you need. And this equation, let me box that in up above, because this equation is on your reference chart, so you do not need to memorize it. You just need to remember when to use it instead of molarity. So now we're ready to go to calculations involving freezing point and boiling point. A couple of things before we get to them. First of all, these calculations are only going to be done for what we call non-volatile solutes. These are solutes that don't evaporate. Because if these are going to evaporate during the course of your experiment, the concentration is going to be changing. Don't evaporate. And these then are usually going to be solids. So most of the time, we're going to see solids involved in these calculations. The other thing we need to do is introduce a new concept called the Van't Hoff factor. Yes, that's how you spell it. And Van't Hoff factor is given by lowercase I. I know in math, lowercase I is the square root of -1. This is not the square root of -1. This indicates the number of particles that are formed when a compound dissolves. The reason for this is because, as we said at the beginning of colligative properties depend on the number of particles in solution. Well, the number of particles can depend on whether or not you break up into ions. For molecular compounds, these are things like sugars, specific kind of sugar, C5H10O5. I don't know, anything that has lots of C's and H's in it. Oh, let's say C8H10. That's actually a particular compound as well that will dissolve in non-aqueous solvents. So for molecular compounds, let me also put after here, or non-aqueous solvents. In non-aqueous solvents, then you don't dissociate into ions. And since you're not dissociating into ions, then one molecule gives you one particle. And that's all you have to worry about. But when you have ionic compounds, and these are going to be ionic compounds in aqueous solutions, then the number of particles and the I depends on your formula. So for KBr, we have two ions. We have K and Br. And so the I factor is equal to 2. For magnesium chloride, we have one magnesium. And remember that 2 doesn't mean a Cl2. It means we have two chloride ions. And so we have 3 ions from MgCl2. And that gives us a Van Hoff factor of 3. So now we're ready to discuss actual calculations here. The boiling point elevation calculation, the delta TB, delta T, change in temperature, B is the boiling point, is equal to the Van Hoff factor I times something called the boiling point constant. KB is the boiling point constant. And then we're going to multiply that by the molality M. And then if we want to know what our actual boiling point is, the TB, that's going to equal our standard boiling point, a little 0 up at the top, that T naught. That naught indicates standard conditions. So those standard conditions would be basically 1 atmosphere pressure, which is what the boiling point is going to be. And since it's an elevation, we're going to add the delta TB that we calculated. And as I said, sorry about that. As I said, the boiling point constant, what's going on? This boiling point constant it depends only on the solvent. So for water, it's always the same for any solvent. Freezing point depression is a similar calculation, except now we're going to call it the delta T sub F, and that's going to equal the I, and now we have a KF, KF being the freezing point constant. And again, we're multiplying by molarity. Oh, by the way, the KB and the KF, the units for KB and KF are going to be in degrees C per molal, because we're multiplying by the molality. And as before, we're going to get that the freezing point now is equal to the standard freezing point minus the delta TF. And we're subtracting because the freezing point is going down. Now, one of the things I do expect you to remember is the standard freezing point of water and standard boiling point of water. So remember that for water, TB naught is equal to 100 degrees C. I'm not putting a decimal point after that because this is a defined number. And the TF is equal to 0 degrees. TF naught is 0 degrees C. So make sure you do remember those. I won't be putting them into the problems. So our first question is we want to find what the freezing point of a solution containing 50 grams of NaCl and 250 grams of water. First thing, separate out the solute from the solvent. So here's our solute, the NaCl, and the water is the solvent. It's usually going to be pretty clear. And here's the freezing point constant for water, 1.86 degrees C per molal. Find M first. To find M first, we got to find the moles of the NaCl. So the moles of the sodium chloride, we have 50.0 grams. 1 mole of sodium chloride, and molar mass 58.44 grams of sodium chloride, and that gives us 0.856 moles of sodium chloride. The solvent, that's going to be 0.2500 kilograms of solvent, and do that calculation. And finally, the molality now is 0.856 moles divided by 0.2500 kilograms, and that equals 3.42 molal. Now, for sodium chloride, we have 2 ions, sodium chloride. The I factor is equal to 2. So the delta TF is equal to 2 times 1.86 degrees C per molal times 3.42 molal. And our delta TF is then 12.7 degrees C. But remember, that's the delta T. We want to get to the actual freezing point. I want to know what the actual freezing point is. So for this solution, the freezing point is equal to 0 degrees C, the standard freezing point of water, minus that 12.7 degrees C, or nice easy calculation, negative 12.7 degrees C. And so this is a solution that we could have used in our demonstration the other day with the seltzer water, because this would get us down to a temperature of negative 12.7 degrees C for our ice bath. Anytime you have an ice bath, the ice and the water that it's in are always at the same temperature, and this is a way to get to a lower temperature ice bath. Now, another cool thing about molality calculations is that you can use them to determine the molar mass of your solute. And the way it's going to work is this. It's a 3-step process. If you take your solute and you dissolve the solute into a solution and you measure either the freezing point or the boiling point. So we're given the mass of the solute, we'll know the mass of the solute, know the mass of the solvent, and we'll know either the freezing point or boiling point. We're then going to be able to determine the molar mass of the solute. And here's how that's going to work. And by the way, these two problems are where you might be seeing some non-aqueous solutions, and that's what we have here. So we have now benzene as our solvent. And we have an unknown non-volatile molecular solute. When you see that, that tells you automatically that the I is equal to 1, a molecular solute, and it's non-volatile again for what we discussed up above. It can't evaporate. And, oops, sorry about that. We have 13 grams of the solute. And what we want to know is what's its molar mass. Now, we have the delta T. We have the TB, and we have the TB naught. Right? I gave you both the TB naught, or actually I gave you the delta T. I gave them both of you there. So the delta T, remember this is boiling point, so it raised the boiling point. The delta T is 80.61 degrees C minus 80.10 degrees C, or 0.51 degrees C was our delta T. A couple more sig figs here because otherwise we're going to be down to 1 sig fig. That's why I took the temperature out to 2 decimal places. From the delta T and the KB. So remember that the delta TB is equal to I times KB times the molality. Well, we have the delta T, we have I, we have KB. So that means the molality of the solution is equal to delta TB divided by I times KB, or 0.51 degrees C divided by I is 1, and KB was 2.65 degrees C per molal. And the degrees C cancel out, leaves us molal in the denominator of the denominator. As we discussed before, that comes up to the numerator. And so this becomes 0.192 molal. So far, so good. We're going to take that number now. And remember that molality is equal to the moles of the solute divided by the kilograms of the solvent. But we know the molality and we know the kilograms of the solvent. We had 500 grams of benzene, or 0.5 kilograms. Rearrange and we get that the moles of the solute is equal to the molality times the kilograms of the solvent. In this case, molality 0.192 molal, and the molality and molality. So let me do that again, because it's going to be moles per kilogram of solvent multiplying by 0.500 kilograms of the solvent. So that cancels out, and we get a molality of 0.0962 moles. Sorry, not a molality. That's the number of moles. Now let's put it back in here. We don't know what the solute is yet, but we know the moles. Now, last thing, the molar mass. And if you remember from previous classes, molar mass is simply the number of moles in a given sample divided by, the other way around, the number of grams in a given sample divided by the number of moles, grams per mole. I gave you the grams up above. That was 13.0 grams. We're going to divide that by 0.0962 moles. And when we get our final answer, we get 140 grams per mole. And you know what? We can put a decimal point at the end of that 140 for 3 sig figs. Actually, no, we shouldn't do it. Sorry, sig fig mavens. I kept 3 sig figs throughout here, but really up here, we should only have 2 sig figs going all the way back to the temperature. So 140 grams per mole. And now you calculated the molar mass in a way other than with the gases. All right. So this is molality and freezing point depression, boiling point elevation calculations. Please go do the homework, do the worksheet, and I will see you in our next meeting.